Hey everybody, this is Larry. This is me doing the fifth weekly premium question, Game of Nim. It's a premium question, premium problem that I haven't solved yet. So let's take a look. I mean, I am familiar with the title, or like I know what a Nim game is. So we'll see what's the situation here. 1908 Game of Nim. Alice and Bob take turns playing a game with Alice starting first. Also, hit the like button, hit the subscribe button, join me on Discord. Maybe I already said it. I'm having, I don't know, old people problems with memory. Anyway, in this game, there are n piles of stone. On each player's turn, the player should remove any positive number of stones from a non-empty pile of his or her choice. The first player who cannot make a move loses, and the other player wins. Given an integer array piles where piles of I is the number of stones in I pile, return true if Alice wins or false if Bob wins. Okay, so let's see. I mean, this seems. Oh, why is my finger so dirty? Okay, so you basically want to take the last pile, maybe, right? Here you have to do. So what is the math here? Let's see. Well, the math is that there are only 7 piles and each one can have 7. So I guess you can probably brute force it, but. And yeah, maybe I think the follow-up is kind of alluding to it, because I was looking for this is a thing that is called game theory, and I was kind of already thinking about a game theory thing. So the one that they probably are asking for, given this follow-up, is kind of and this is something that you can look up, Minimax. I don't know if it's called Minimax. I mean, it is with a more binary scoring function. We just read up on this, which is and you can kind of basically brute force like given I am Alice, or it doesn't matter the person actually, given that I'm the person playing at this turn, and the current states, how do you say it, and I take X number of rocks or whatever it is, from a pile, what would can I win, right? So basically you brute force that, and there's some dynamic programming with memorization and stuff. Memorization. Yeah. Well, I don't know what I'm. And if I get a stroke on camera, please let me please let me know. I don't know. But anyway, okay, so yeah. So Minimax, we'll kind of read up on that. That's kind of like a thing that's, I wouldn't say it's common, but it is something that does come up from time to time. So I think, to be honest, if you ask me, I think that that would be beyond the scope of an interview, but I don't know. All right, so I am going to try to see if I can find a linear time solution. And this is basically, there are really 2 ways to maybe think about it, but also maybe not. Basically, there is this thing called numbers, and part of that is gonna this thing called max, which is maximum excluding, is what it means, of these numbers. I don't think I don't know. You definitely could solve it using numbers, but I'm just trying to think whether there's a more it's just a more straightforward way to kind of interpret this, right? Like I think we can work backwards a little bit, right? So basically, if there's one pile, let's think about it backwards. If there is one pile, and it's my turn, I win, right? Because if there's only one pile left, then I take everything, and then if I take everything, so then the next person goes and loses, right? What if there are 2 piles, right? If there are 2 piles and I take everything, then the next person will obviously just remove everything from the one pile and then win. So then what I want to do is basically, let's just say for whatever, there's 7, right? I think the number doesn't actually matter, because I don't think, I don't know, maybe it does. But for now, let's say there are two piles, right? If I take all of 7, then the next person, Bob, takes, or Alice, or whomever I'm playing, because I'm Larry. Uh, and then, you know, they would win because then I go after that, right? So what if we... So, okay, 2 piles is losing. Why do I say that? I was going to make an argument about what happens. Maybe I would do it anyways. So yeah, because then the idea is that, okay, what if I took, you know, let's just say maybe an obvious next move is, let's just say there's 7-7. I take 6 from one of the piles, right? Obviously, it doesn't matter which one. They all similar, right? Then the thing is that, well, if I'm Bob, I just match it, right? I go to 1, and then now I have to take one of the ones and then 1, and then they win. And I think it doesn't even matter. Well, so if the 2 piles like that is matching, but let's say it's 7-5, I take 6, and then they would just take it to match. So that would also be losing, because if they could match, then they could keep matching, right? What if it's something like 4? Then, oh, then, or maybe even no. That 7-5, I'm winning because I can just take 1, and then I'm matching, right? Because then now whatever they do, you know, they take 5, I take 5. They take 4, I take 4. The logic about this matching is that you will always have a move because you're just copying what they do, if that makes sense. Because if the opponent has a move, then you have a move because you're able to match all their moves. So, okay. So basically, if there are 2 piles, if the numbers are not the same, I win. If they are the same, I lose, right? That's basically the logic that we're at. Hope that kind of makes sense. Okay. And then now, what are the 3 piles? I kind of already have an idea, to be honest, but let's kind of let's kind of keep looking for a little bit. All right. And we'll play around with, let's say we have this, right? Well, the matching thing doesn't quite work anymore. What would be the move that I do? Right? Let's say I take all of this, then Bob will... No, well, if this is the case, then I take this, then now the numbers are the same, but Bob goes or Alice goes, then now I win because I can match, right? So if there are 3 piles, if 2 of the numbers are the same, then I win because I can take 1 pile, right? But what if they're not? Let's say we have 4, 6, 7, right? Well, if I take 1 pile, then they win because they can do it. So then maybe my thing, what if I did 3, right? Then what happens? Then they can't really do, can they do anything? You know, let's say I reduce this here. Then, obviously, if they do just something like 6, then we remove this and then we match. If they do remove 6, then we remove 6 from here and then we match. And then maybe we, I don't know, well, you take like 4 for some reason. Then they take the 1, then we take the 3 and then you win, but then they wouldn't do that then, right? Maybe they take the 3, you take the ring, and then, yeah, then they would take the 3 and then you lose. So in this case, and then they go, and they win. So you wouldn't do it. So, well, this is a losing state. So one thing that you can kind of think about, and this doesn't really, this is a kind of a next level thing only because I know a bit of game theory, is that you can actually rethink about this as, you know, instead of matching, so, you know, you have this idea of this matching with two powers, right? If you can think about this in a weird way, or not a weird way, but you can think about it instead of powers of 7 and 7, you can think about it in a binary number kind of way, right? You have 1, 1, 1, and then you have 1, 1, 1. Two powers of ones, right? So something like this. And the idea here is that when you take a number, you can basically take a binary component of this, right? So that you can kind of match, right? Because basically, what does that mean, right? By matching, this idea of matching is that if they take 6, that means that we just convert the first 2 to 0 and so forth. The idea isn't that important for 2 piles, but I think it is something that you can generalize into 3 piles, right? Because now you have 1, 1, 1, 1, 1, 0, and then 1, right? 0, 0, 1 maybe. Because then now, the idea is that, well, this is a losing state because this is a losing state because whatever I do, they can match, right? If I take this 1, they'll just take this 1. If I take this 1, then they'll just match by doing this 1. If I take this 1, they'll match by doing this 1. And also, as you can see, after that, well, let's say I took that 1, which means that I remove 4 from either the 7 or the 6, it doesn't matter because they'll take it from the other, then this is the new state. Then, you know, if I take this 1, they'll match and match, right? That means that for every move that I do, they are able to match. And that's basically this idea of a parity on each binary digit, right? Okay, so given that, what you want to do in a generalization thing is basically you have an XOR is equal to 0 for x in piles, XOR of x, if and then you just return XOR is equal to 0, right? This may, I don't know if this seems like a jump, but yeah, maybe 0 is a losing state. Sorry, for me. If I so yeah, yeah, okay. But basically the idea is that if you kind of think about it through the binary states, then if they're even numbers in all the digits, then that means that whatever I do, they will do the same thing from some place, right? How how do you do, like, if I, what if I remove all 3? What would they do? That's interesting. And what if there's an extra digit, right? Then when we move all 3, and how do they match? Kind of missed this part about it. Sorry, thinking it for a second. I'm basically, I mean, I'm honestly just like reinventing. I don't know, reinventing, rediscovering game theory from first principles. And I'm kind of, it's something that I haven't done in a long time. So it's kind of, it's amusing and fun to me. But I am trying to remember this, or like, what would be, what if I remove right? What would they do? They would, in this case, I guess remove one of these. and then I would remove one of these. I don't know actually. That is a good question. Because that's basically 15. Was it 15 minus 3? So 12, and this is just 3, right? What would you do if I just remove this 15? Well, then it's their turn. Right? It's their turn, and it's this. This is basically a winning state for me, but I don't know how. It's either that or I made some mistake, but that's also possible. How is this a winning state? Oh, I am dumb. I see. I that's what happens when you get too much into the binary. But basically, I can remove 9, and then now it wouldn't just remove the ones, but it will also convert these two to things, and then now you just matched again. Okay, of course. But I think I was too. I was trying to think too much in my head where the digits are independent, and you can certainly look at it that way in a lot of cases, or at least as a basis for kind of thinking about the digits independently, but they're not fully independent. You would just remove 9, and then you have 3, and then you're able to maybe the right way to say it isn't necessarily and you in theory you can also do the same here, but obviously you can because you can add pile, but you by definition of if the parities are 0 at the end, or like at the beginning rather, that means that there are at least 2 other digits that match these 2 ones in those digits anyway. So that means that that's always possible. Okay, now I'm convinced, and hopefully that was a good illustration. I think I kind of futtered a little bit on the original kind of visualization, but yeah. Okay, cool. I mean, I think I'm pretty happy with what I did here, because I think you will see this from time to time randomly, and a lot of people just kind of YOLO doing it without a deep understanding, me included, on a contest. Not gonna lie, but because I kind of, it's just things that I've done like decades ago. So trying to kind of prove to myself that things work, and then this idea of matching and evening means that force it in a way such that you always have a move, because you're literally copying the other person, right? And then and then you can make the first move such that you can get it into a state where you copy a person. Then yeah, and the reason why this XOR is not equal to 0 is because this is a losing state. Because if XOR is 0, then it's a losing state, because whatever you do, they will copy if this is your turn. So then if it's not 0, then we can remove the right amount of stones such that the XOR can be 0. And that's basically the idea, which I kind of confused myself, so I didn't really talk in detail, but hopefully that kind of makes sense. Cool, that's all I have for this one. Let me know what you think. There is a lot of, I mean, I know that I kind of maybe hand wavy a little bit about here, to be honest, but it is I hope this serves as a good introduction for number theory, or game theory. Yeah, and you can certainly do it the other way, because there are only 7 piles. What is 7 to the 7 anyway? I don't. 823,000 should be good enough. Though technically, I guess it's 7 to the 8. In some language, that'll be fast enough. Cool. Yeah, but also like the follow-up said, this is not in the scope of an interview unless you're being an economist or something. So yeah, that's all I have for this one. That's all I have for this premium question. Let me know what you think. Let me know your questions. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.